So I come from a department called astrogeophysics. You may not be familiar with that, or some of you are truly familiar, like Kim Melville, because it was the genesis of really a department in the University of Colorado and of HAO. We shared the same building. When I came on the scene, the Duane Physics Complex was just opened, and similarly the Gamow Tower went up, and we moved out of tenancy in the same building. There was some causality, on the other hand. When I arrived, Peter Gilman decided it was time to go join NCAR, just to make sure that the number of people interested in sort of convection or so was preserved. But I thought it was appropriate to bring along a little bit of a present. And this is the original sign of astrogeophysics, which I inherited from a faculty member once he gave up his lab. So, yay. And perhaps I should hang it somewhere. I may not be able to hang it anywhere, but it has hooks and other silly things with it. Perhaps we can just hang it on a... I was thinking of how you might hang it. Oh, maybe you can hang it here. Or maybe we can't hang it. Well, how about that? Anyway, the department and HAO have shared beginnings, as we heard yesterday in this absolutely delightful and very detailed talk. But my job is to tell you about a few of the things that have gone on since then that touch somewhat on helioseismology, about numerical simulations, and similarly on dynamo calculations that have proceeded. Of course, our inspiration has been essentially this picture. We've heard a fair amount about it. The most significant aspects of this evolving pattern, basically more readily available to us because we have spacecraft to sample the sun, is that there is apparent equatorward propagation at low latitudes of the fields that emerge, and also fairly significant field that seems to migrate to the poles. And of course, a challenge to us is to fundamentally understand how does this come about? What in the inside of this astrogeophysical thing is doing its bit? Where we have some advantage over astrophysics is that we do live next to a star that we can see in fair detail. It's supposed to be kind of an ordinary runt of a star, and it's kind of interesting. The American Astronomical Society views it as just one of 300 billion stars in our galaxy. So what's special about it? The geophysics community seems to view it as our star. And it's interesting, we, as a department, try to foster on the world the idea of somehow astrogeophysics. It didn't take on. We are now called the Department of Astrophysical and Planetary Sciences, and we had some things further along the way. I think only one department adopted that name, and that was in South Korea. And they may have given it up since then. On the other hand, we also welcome the idea that people who work in solar physics or helioseismology are recognized, as your former director, Michael Thompson, to become a fellow of the AGU. And geophysics comes certainly into that title, and Jim Hurl knows this very well. I'd like to spend of the order of one solar oscillation talking a little bit about, just reminding you of some things about helioseismology, because it permits us to look inside the star, which is also an exceptional possibility. Many of you know a great deal about this, and in our audience are some very significant people who made this subject happen. Douglas Goff, Tim Brown, Jack Harvey, and your eminent former director, Michael Thompson. But the game is more or less the following, that the sun generates sound waves in the intense turbulence of the surface, which is able to, in fact, excite genuinely millions of modes. They bounce around inside the sun, and they are able to leak into the atmosphere where we can see them. They actually get reflected below the surface for the most part. The ray paths can be fairly shallow things, or they can go right through the center of the sun, bounce off the other side. We would love it if the sun also had internal gravity waves, which occur below the convection zone. Unfortunately, we haven't been able to actually detect them. They probably are there, but they get severely attenuated. If we had the ability to see that, we'd also be able to probe in much greater detail what goes on in the nuclear burning region within the radiative zone. The subject itself started quite some time before 1990, but particularly in 1990, there was the initiation of a major community effort to get together at the Institute of Theoretical Physics, now the Kavli Institute of Theoretical Physics in Santa Barbara. And we learned a great deal from geophysicists about their version of earthquakes, our version of sunquakes. Where we differ is the sun is resonating continuously because it's these small ball-peen hammers of granulation that are exciting all these modes. Unlike in the Earth's resonances, it's sort of a major earthquake event that most geophysics looks at the arriving waves. A few look at the final very low resonances that are established in the long term. But that methodology gave us significant beginnings. I should say that at the end of this 6-month period at ITP, and throughout also earlier, there were major workshops here at HAO. HAO was a significant participant in this entire venture through its visitor program and other staff members and postdocs and students that they trained. But at the end of this 6-month period, 2 things happened. The largest fire in California, in Santa Barbara, that burned down about 600 homes. That's a pretty good, surprising end to a scientific program. And the other thing is we launched Hubble Space Telescope. And this evening, John Grunsfeld will be speaking about that. He was not involved in the first putting Hubble into orbit, but he visited Hubble 3 times subsequently. And I think it would be a fascinating talk. He's a high-energy physicist, trained in Chicago, from a family of architects, whatever that means. History is important, but his grandfather designed the Adler Planetarium in Chicago. He's currently the director of the Science Mission Directorate, associate administrator, which means he's the boss of all science for NASA. And it influences, we'll see what he may have to say to us about funding plans and other things like this. The oscillation modes have all the sort of beautiful, simple properties of spherical harmonic functions on the surface and a number of different wiggles, reflection points they can have. This is one of the millions of modes. Each has a slightly different tone. We can use them to do some mischief. It required, on the other hand, being able to observe the sun continuously, and it came about in 2 ways. One was the so-called GONG network, or Global Oscillation Network station from the ground, that used analyzers that are about the size of a quarter. They cost rather more than a quarter. For $30 million or so, we put together this network, and it's still functioning. Significant activity of the National Solar Observatory. And for people who had rather more money, we also launched a solar spacecraft, now the Solar Dynamics Observatory, with essentially the ability to image the sun at first 1,000 by 1,000 pixels every 30 seconds or so, in a number of different wavelengths, using Fourier tachometers and Michelson interferometers and things like these, Doppler imagers. But what it provided was continuous observations of the sun in line-of-sight Doppler velocity. But if you analyze them in terms of what each possible surface mode could be doing, you found that the power remarkably was in these ridges of angular degree, how many wiggles you have in the horizontal versus temporal frequency. And it looks a little bit like just a beautiful structure. We're able to get physicists to be absolutely enthusiastic about it because it seemed an improbable thing to do, and there were things that we could answer with if we could measure these modes. And if you're in the spirit of counting anything, we can say this is the fundamental mode P1. These are different resonances. We're going to higher overtones in the radial direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, a little bit like fishermen talking about the size of their fish. There are lots of ridges, but these are, we're seeing a signature of the order of 1 million modes. If we use about 10,000, 100,000 of them to make some deductions, the deductions that really emerge are that we're able to see how the sun rotates within its interior. And this is a crucial matter because although we've known for a long time that the equator rotates reasonably fast and the poles fairly slow, by seeing what happens with these magnetic defects, sunspots and other things that emerge. But here we rotate around 25 days and about 33 days up at the poles. But helioseismology showed us that through the bulk of the convection zone, what's more or less at the surface prints through, roughly on radial lines. They happen to be maybe more conical surfaces, until you reach the bottom of the convection zone, and there you go into uniform rotation of the deep interior. And that region has come to be called a tachocline, tacho for speed, cline, a layer of change. Thermoclines in the oceans are one example of a layer. And so what is remarkable is that we have essentially a few things. Few had anticipated that the interior would be rotating at roughly the same rate as the outside, but with no differential rotation. And that there existed, in fact, a layer of change which shows up a little bit better if we took a series of cuts at different latitudes, which would give us a view like this. So there's a function of depth and what the mean angular velocity varies, how it varies, that we have a boundary layer of speed up of rotation just near the surface, which has come to be called the near surface shear layer, almost uniform, not quite, rotation, say at 30 degrees, and all of these branches come together at the base of the convection zone. Now, they're likely to come together into a much narrower layer than shown here for the tachocline, maybe only 1% or so in thickness. Here it's about 5% in proportional radius, partly because of the resolution that's available in the inversion of this data. But this is our challenge. Do we understand how this comes about, among other things? And why is it there? And the focus of the current Solar Dynamics Observatory is very much, among other things, to study the dynamics that occurs in this particular boundary layer. In addition to the so-called global helioseismology, you can also carry out investigations in localized regions using time-distance methods or ring diagrams. These are just technical definitions, but using the local properties of the wave field that is very rich. And from it, you can deduce that, for instance, 1% of the way into the sun, 7 megameters, so-called, there are large streaming motions that amble back and forth a little bit like jet streams, and they certainly interact in substantial ways with the magnetic features that you have seen at the surface. So we're a little bit like we have been for now some time at this unusual business. As the first weather satellites came into meteorology, you began to see the larger patterns rather than where was a given front. We're able to do this also, and it's quite clear that there are intricate interactions, and they can be done with much more exquisite detail of where we're looking, and at least within the sort of near surface shear layer. After that, our vision gets sort of fuzzier, largely because the resolution of the modes that you have available changes. Well, fine. Well, that was a little bit more than one oscillation's worth of 5 minutes. But so what we have is a magnetic star that has basically two subtle boundary layers. One near the surface, one deeper down. The deeper one maybe I should really mention first, the tachocline, has often been thought to be the seat of the intricate operation of the global dynamo. But what is its structure? What is its variability? The near surface shear layer, it is certainly the residence home of most of the features and structures that we see that emerge. How is it formed? What is its dynamic role? These, in some ways, would be the questions that inform us. And if we said, well, what are the challenges to convection and dynamo theory? It's basically these three questions. How is it that the differential rotation is maintained all continuously? It doesn't seem to change very much. How do you build the fairly orderly bands of toroidal magnetic fields that appear to erupt as sunspot pairs that Sarah was showing us? And why is it that there's a global dynamo in some fashion operating that has reversing cycles of activity? Now, these seem friendly enough questions. The difficulty is that this domain of the convection zone is among the most turbulent system in our near universe. Probably all stars share it that are similar in mass to the sun. But how does it operate? Why is it that you get orderly behavior for something that is an extremely turbulent, complex system? Now, of course, you might say order should be able to emerge out of chaos when we use simple models that is present. But there are a huge number of temporal scales and spatial scales involved in this. Why does it behave the way it does? So the procedures have been to say, well, let's work in this third branch of astronomy, which we might call computational astrophysics, in addition to theory and observation. And let's look to see, can we build some global circulation models of one sort or another? I'm involved with a happy crew called the Ash Mob. Whoops, the Ash Mob would like to go back again. Whoops, excuse me. That involves really significant participation between the university and HAO. But we're building basically on the shoulders of Peter Gilman and Gary Glatzmeyer. It's a code that can look at models within a full spherical shell. There are other three-dimensional codes that have been developed most recently here at HAO by Yuhang Fan and Hata and Rempel that I'll also show you briefly in just a few minutes. But let's see what we get. So if you turn on one of these simulations, and we're in a co-rotating frame of the sun, we're looking at the radial velocities, but it's quite clear, and the equator is shown here, that these things are marching to the right and these things are to the left at high latitudes. And this is an example of where the convection itself establishes strong differential rotation. It isn't that it's simply being carried, and it's being maintained by the Coriolis forces acting on this fairly substantially complex fluid motion. If we look at this in a world view, this is a little bit like the cosmologist's view of the universe. It emphasizes that if this is the equator and these are the poles, that there's some organized north-south aligned with the rotation structure to this snapshot of velocities. These deep motions know that they're on an object that is rotating. And this type of a simulation is able to capture fairly well the differential rotation of the sun, similar in contrast, and we're sort of cherishing this as we've begun to crack the problem. On the other hand, if we go to higher resolution, an example of a snapshot from that is here. Its Mollweide view looks like this, but if we have that thing running away, both sampling things near the surface and deeper down, again, radial velocity, it emphasizes that it's really a radial conductivity of downflows across the full convection zone. We've just chopped off the top and bottom to have these movies fit on the same space. But it also says that as we went more turbulent or more complex, we reduced the diffusivities, we also ended up reducing the differential rotation we could maintain with these flows. So it's kind of curious. There's a technical language. There are effects of rotation by the Rossby number were probably reduced. And remarkably, by paying more and doing more, you get slightly weaker differential rotation. In fact, it's possible, if we follow this path, to get to the point of where the sun begins to get anti-solar rotation, where the equator is not fast, but rather slow and flips. And the sun has one problem, or maybe we have a problem. It rotates too slowly. It currently rotates at only 2 kilometers per second, tangentially at the equator. Young stars do 120 kilometers per second. The sun has really been spun down to the business where it's quite challenging for us in some ways to capture issues of differential rotation. We can get around that by rotating the sun a little bit faster or reducing its luminosity, the energy flux to be carried by the convection. But there's an interesting sort of challenge associated with that. If we go to look at dynamo action, maybe in a slightly younger sun rotating 3 times fast, the radial velocity again emphasizes in this Mollweide view, we have fast equators, slow poles, fast equator means marching, these patterns are marching to the right. If we ask, well, what type of magnetism do you build with these models? This is the east-west toroidal magnetic field as a function of time as this thing is running. And what is emerged from this is that the magnetism that you build tend to be within the convection zone, big bands, which we almost call wreaths of magnetism. And red is of one sign, toroidal field, blue of the other. And it's quite clear that this thing is cycling. Not entirely tidally, but it goes through reversals and has another sort of series of properties with it. And the magnetic fields, if we image them in the interior, have these sort of wreathy structures. They look a little bit like great balls of spaghetti that's been put together. But that is a surprise that in the bulk of the convection zone, where we thought that magnetic fields could only be built at the bottom of the convection zone where things were quieter in the tachocline, that the bulk of this highly turbulent system can build you fairly organized wreaths of magnetism that has certain rules. Now that was a delightful surprise. It isn't the sun, it's a thought experiment, an expensive one, but that the bulk of the convection zone, which is highly turbulent, is able to build large-scale coherent structures. And if you look at these structures in detail, they're not simple tubes. The magnetic field comes in and out of these concentrations. We're looking at a small section here that's really this portion of a big Mollweide view that you've been now trained with. And if we said, well, let's do something nervous and show you a movie of what happens with magnetic field lines as this thing is advancing. We've cut away some of it so you can kind of look into the heart of it. But this is the bulk of the convection zone. And we're hanging in with red here, and it's going to start changing. So this is with the ASH code. It may make you nervous just because the jitter is that you shoot magnetic field lines and these are just entities in themselves. But it emphasizes that things are certainly evolving and changing. Further, from portions of these wreaths, small loops can break off all by themselves and then rise toward the surface. And if we track them, they're partly magnetically buoyant. They're partly also carried by the upflows of these large convection cells. So it's a bunch of pleasures. There's been substantial progress in dynamo theory in the past 5 years or so by about 4 different groups. You can get, with the sort of things I showed you, you can get persistent wreaths that hang in there. They're ones that go through cycles. Major work by Paul Charbonneau and company with using an Euler code that shows you can get repeated cycles. Again, loops break off from places. Axel Brandenburg is here and will be for the next 3 years. He and his crew have been working with another code called Pencil, which again shows a number of properties, including equator propagation. So it's a bubbling time of dynamo theory. We're not getting any of it really absolutely right, but there are many hints. Let me just finish by just showing you 3 current calculations. One of them involves using ASH. Carl Augustin was a lead on this, but using some of the techniques that Matthias Rempel invented in terms of how you treat with diffusion, called slope-limited diffusion. The snapshots of the radial velocity in terms of complicated flows looks like this. But if we let this thing run, here is a Mollweide view of the toroidal magnetic fields. Again, you begin to now see wreaths forming, but they march along. And here's the time slice of what the average field looks like east-west. Equator is here, north-south latitude, and it marches along. And what is remarkable with this movie, this thing cycles and cycles and cycles. It has periods of about six years, not 11, but never mind. And the other unusual thing with this is that some of these cycles, which repeat, it actually turns itself off, or seems to. It goes into a minimum and then restarts. and we didn't tickle it. And if we ask, well, what does this look like? Well, in the middle of this minimum, we've essentially gone from something where the dipole moment, which is in blue, the dipole moment basically becomes of just one sign during this minimum, whereas the quadrupole moment keeps still operating. So we also believe that during the Moulder minimum, the sun didn't turn itself off in magnetism, but it changed its possibly reversing cycles. Well, it's interesting. Have we captured the grand minimum? Well, probably not. We got the wrong periods. There are other things like this, but there are certainly tempting aspects. There are two codes that I'll finish with. Yuhang Fan has done heroic work with building an alternative type of a code called FSAM, and she and Fan and Fang, Yuhang Fan and Fang Fang, but Fang Fang is getting married, so maybe Fang Fang will have a different name, or maybe not. But their machinery also is yielding very interesting sort of cycles, not quite so regular, but there are many sort of temptations associated with it. And in fact, if we ask, well, what's the nature of the magnetic fields that are built in the interior, they have loops, fairly complicated structures, but we're getting to this business of where we have essentially tools for sampling things. Probably the hero calculations of the day right now are the work of Hideyuki Hota, who was here until last week, Matthias Rempel, and their colleague Yokoyama, using a different code, a version of the sort of techniques that were shown to you with sunspot modeling yesterday by Matthias. They found that if they ran their model at different spatial resolutions, in low resolution, it would give you roughly repeatable reversals. As you increase the resolution, but with it also substantially reduce the diffusion that goes along with it, it lost its way. It became much more random. But if you went to even higher resolution, it came back to have fairly interesting sort of repeatable cycles. And the message from that is that if you go with these techniques to lower diffusion, you also begin to initiate small-scale dynamo action throughout the bulk of the convection zone. And perhaps the real message is that we shouldn't be talking about a hydrodynamic sun at all. Maybe we should be talking about it. All stars, including the sun, has small-scale magnetic chaff everywhere that changes the effective viscosity or diffusivity, gives it a certain stiffness, makes it almost look like a more diffusive system. And I'll just finish with their heroic movie that only cost you probably $2 or $3 million to make. I think it's of Japanese money in this one, but fresh off the press, and I think it's being considered for publication in Science. But it shows you their highest resolution simulation, which can come back to having cycles. But you see, it's complicated, and probably the sun is even more complicated. So where are we, besides my running out of time? Well, here's the state of play with dynamo modeling. In a way, there's a big hurrah which says that, look, we're able to begin achieving cycling dynamos with regular reversals in one form or another. And it's being achieved with a number of self-consistent convection models, different treatments. So we have a tool for thinking about things. I mean, it really is a laboratory tool that may begin to complement some of the constraints we put onto it from helioseismology. The results are, however, all the results are fairly sensitive to what you do with what you might call subgrid scale transports. There's smaller scales that you're not able to capture. And still, although I said the sun has two boundary layers, we still haven't really sorted out the role of the tachocline and near-surface shear layers. We have ideas, but these have yet to be systematically tackled. And so the sun in astrophysics is referred to as a very modest, ordinary magnetic star. In fact, they often forget that it's magnetic. It is, however, highly turbulent. And I would say that in the score of things, the sun is still winning. I mean, we have the privilege of trying to nibble at it, but its mysteries still are fairly abundant. However, there have been fairly striking advances as we nibble away on it, and that's probably worthy of HAO and us, the rest of us, going on to our 76th year. So thank you very much.
Thank you, Yuri.